All right, we're going to start chapter 9.3, and we're breaking this into 2 days of notes. So today we're going to talk about the integral test. Tomorrow's the P-series test. So we've talked about so far the nth term test for divergence. So that was where you do kind of a mental check. Make sure the terms actually are approaching zero, so you have a chance for a convergent series. And if they're not, then you know the series diverges. Geometric series, telescoping series, and we can apply those tests to any series as long as they're in a geometric form or in a telescoping form. So there are several tests that we can use as long as we know all of the terms in the series are positive. So the first test that we're going to learn today is called the integral test. And I just want to put a couple of disclaimers here. This should be the last test you try. We're going to learn a lot of different tests this chapter, and the last thing I want to do is have an integration problem. So there are some problems that can be tackled with a few different tests. If you have the option, you would not choose the integral test if you can avoid it. All right, so you might need to pause the video to write this part down. If our function f is positive, continuous, and decreasing on the interval x greater than or equal to 1, and if the sequence is equal to f of n, so let's do a quick picture of what that means. Give yourself a sketch of a positive decreasing function. Mine just looks like this. That's f. A sequence, remember, is just saying, okay, at 1, there's the first term of my sequence. And at 2, here's the second term, at 3. So when we say we want our sequence to equal f of n, we just mean the terms of the sequence are equal to that exact point on f of x, right? You're not going to have a point that's like way up here. Okay, so anyway, that's what that picture is saying. Then the sum from 1 to infinity of the sequence, so the series, the sum of these blue terms here, and the integral, the area under the curve from 1 to infinity, f of x dx, they either both converge or they both diverge. Now, visually, you can kind of see this easier. Is the area that I get underneath the curve of f of x, is that going to equal the sum of these finite points here? Visually, that answer should be no, right? This could be like 5 plus 4 plus 3 plus 2 plus 1, something like that. That is definitely not going to be the same as the area I get when I fill in all of that space between f of x and the x-axis. So sure, they both act the same way. Let's put act the same. They either both converge or they both diverge, but they don't converge to the same value. So warning here, the integral test doesn't give sum of series. Only tells converge or diverge. What I mean by that is if you do the integral from 1 to infinity of some f of x dx, and let's just say we get 2 for that area, that does not mean that the sum of the equivalent series, so the series whose points are all on f of x, it doesn't mean that that sum is necessarily equal to 2. All right, but they both converge to a value. Now, this proof is quite formal. Even if you don't have it, I wouldn't take the time to copy it down. You're welcome to. Now, when you're sitting in some college math classes, just know that you're going to get to write all of this fun stuff down, probably as your professor writes it on the board. I will sum up what it's talking about, though, in a very summarized fashion. So let's go back to thinking about Riemann sums. There's a proof of why this is possible. So if we think about our Riemann sums, we had like a lower sum and an upper sum, right? So I have this positive, decreasing, continuous function f, and I can come up with an approximate area by using inscribed rectangles. And you can see this first one starts at f of 2, f of 3, f of 4. So it's a lower sum, and in this case, it's a right sum. So that would have some sort of finite sum. It would approximate the area, but it would definitely be less than the actual area. I can do the same thing by using an upper sum. Some of my rectangles got erased here. You can see this one, an upper sum in this case, starts on the left. So we have like f of 1, f of 2, f of 3, rectangles of those heights. Now that would definitely overestimate the area of f of x. All right, so the exact area between f of x and the x-axis falls somewhere between the lower sum and the upper sum. Instead of just saying the words lower sum, upper sum, we can look at these as summations. It's the sum of the series. Remember we talked about how, back here, we talked about how we could come up with an equivalent series whose points are just points on f of x. So you can kind of see where those would generate, the corners of each rectangle. So we've got the sum of the series on the lower end, sum of the series on the higher end. You can see they're off by one term. This one starts at 2. This one starts at 1. So there's some fancy adjustments here looking at partial sums and how they relate. This is the partial sum minus the first term. Here's a partial sum going to n minus 1. Again, I'm summarizing this in kind of a poor way right now. But anyway, the whole idea is that, hey, if I can come up with this partial sum and I can come up with this partial sum, and I know that my exact area is sandwiched somewhere in between there, if I know that these sums actually converge, then my actual area will have to converge as well, because its lower bound converges, its upper bound converges. There's no way it could just diverge and like break through those fences. All this fun L stuff is talking about how your partial sum, we can prove that it's bounded and monotonic and therefore converges. So again, if you want a more formal proof on that, you would hop on YouTube and type in prove the integral test, and I'm sure you could find all kinds of fun stuff. I don't think that any of you are really going to be worried at the moment about just going ahead and applying this test, figuring out what to do. This is one of the tests that we actually do have qualifications for. Remember, to use the integral test, your f of x has to be positive, decreasing, and continuous. It's something you should check all the time. Now, right now, this is not a function. This is a series. So let's come up with the equivalent function. The equivalent function is f of x equals x over x squared plus 1. Right? This would be the equivalent function. I'm just swapping out n's for x's. So this is continuous. Check. Is it always positive for values greater than or equal to 1? Yes. And is it decreasing? Yes, it's bottom heavy. So this checks all the boxes. It's positive. It's decreasing. It's continuous. Now, if I were doing a free response question, I would write out f of x is positive, decreasing, and continuous. But here I'm just kind of making bullet points. So that means that if I want to figure out whether this converges or diverges, because a quick term test in my head tells me the terms approach 0, I can say, well, this is equal to the integral from 1 to infinity of x over x squared plus 1 dx. And now it's a chapter 8 problem. I can take this improper integral and use limit notation to get rid of that infinity. Maybe a little fancy u sub over here to figure out how to take the antiderivative. So I'm going to do those 2 steps in one. I've got the limit as b approaches infinity of the integral from 1 to b. And then let's see, what integration method are we going to use? We had u could equal x squared plus 1. So that du would equal 2x dx. I have x dx, I need 2x dx, so I throw 1/2 out there. All right, so I got a little ahead of myself writing. I need a 1/2 integral from 1 to b of, I like to rewrite in terms of u, so 1 over u du. That equals the limit as b approaches infinity of what? 1/2. This is going to be natural log of u. Now, I remember in our chapter 8 test, if you forget to put your value for what your u sub is back in, you can come up with the wrong answer. So be careful there. I think a lot of us did that when it was like e to the u and u was actually a negative exponent. So here it's not as big of a deal, but it's 1/2 natural log of x squared plus 1, evaluated from 1 to b. Remember, we don't drop our limit notation until we actually take the limit. So the next step is subbing in b and 1. So 1/2 natural log of b plus 1 minus b squared, technically, plus 1, minus 1/2 natural log of 1 squared plus 1's natural log of 2. 1/2 times the natural log of infinity. The natural log of infinity is infinity minus 1/2 natural log of 2, which is ultimately just infinity. So even though the nth term test showed me that the terms are approaching 0, they're decreasing, the actual integral test tells me that this diverges. So I'm going to write my conclusion right here. So series diverges by the integral test. Now, when I say this should be your last resort, we're going to learn some other tests that maybe we could work with this one on, but I couldn't have done partial sum or anything to try to make it telescoping because that's n squared plus 1, and it's not geometric, so that's why we're doing integral test right now. All right, what about the next one? First, come up with your equivalent f of x, which is really just writing f of x equals replace n with x, 1 over x squared plus 1. Do a quick nth term test. Are those terms approaching 0? Yes, so this has a chance to converge. 1 over x squared plus 1 is positive. It's decreasing. The terms are approaching 0. And it's continuous, since the denominator is never equal to 0. So we can set this up to say this is the integral from 1 to infinity of 1 over x squared plus 1 dx. Limit as b approaches infinity of the integral from 1 to b. So what is this 1 over x squared plus 1? Remember, a constant over a sum of two perfect squares is usually an arctangent problem, right? So so I'm going to write it as 1 over u squared plus a squared du. We don't have any substitutions to make because u is equal to x, du is dx, a is just 1. So maybe you don't even write that little substitution, I don't know. Next step is to come up with the antiderivative. So the limit as b approaches infinity of, now normally arctangent is 1 over a is 1, so I'm just going to write arctangent of normally u over a, but I'll just write x, from 1 to b. Limit as, b approaches infinity of the arctangent of b minus the arctangent of 1. Drop limit notation, plug in infinity. The arctangent of infinity, we've had this a few times now, is pi over 2 minus arctangent of 1, pi over 4. The area under the curve for f of x is pi over 4, but that is not the sum of the series. All this tells me is that the series converges, but not to pi over 4. All right, and the questions will just be converge or diverge. And again, like by what test? So I should have said converges by integral test. All right, what about part C? First of all, this is not geometric. A quick nth term test tells me I get 1 over infinity. So yes, the terms are approaching 0. So this is not diverge right off the bat anyway. My f of x is equal to 1 over x natural log x. And let's see, from 2 to infinity, 1's not in there because natural log of 1 is 0, by the way. Anyway, so from 2 to infinity, terms are positive. They are decreasing. And the fact that we're starting at 2 makes it so that this is continuous as well. All right, so now we can say we've got, I'm going to write my limit notation right off the bat. The limit as b approaches infinity of the integral from 2 to b, just saving myself one little step there, of 1 over x natural log x dx. Now this is a u sub because I can let u equal natural log x so that du equals 1 over x dx, which I have, 1 over x dx. So no extra adjustment needed on this. I am going to write it in terms of u before I integrate. So it's the limit as b approaches infinity of the integral from 2 to b of 1 over u du. That's the limit as b approaches infinity of the natural log of u, but I'm not going to write natural log of u. I'm going to write natural log of x evaluated from 2 to b. So the limit as b approaches infinity of natural log of b minus natural log of 2. Okay, so natural log of infinity is infinity. And the natural log of infinity again is infinity, right? So don't let the natural log mess you up. This is constant, whatever natural log of 2 is. But overall, that's coming out to infinity. So even though the nth term test showed me that the terms are approaching 0, it does not guarantee that that series will converge. If the equivalent function diverges, then the series diverges by the integral test. All right. Now these aren't terrible to do, but again, it should be the last thing to try. We will learn a few more tests where maybe some of these problems can be done in a different way that doesn't involve U sub and all that other stuff. So on our quiz on Monday, your choices are nth term test, geometric series, telescoping, and if all else fails, maybe coming up with some sort of a pattern, but for S sub m, but I don't think that we really have to do that. All right, that's it for today.